We learned all that implicit differentiation, remember, as a skill to allow us to do something called related rates, to apply it in a situation where we're going to take an equation that represents a situation that, x squared plus y squared equals c squared. We did Pythagorean theorem, or we're going to do, I think we're doing another one of those right now, but that's been kind of our common one. There are other geometric representations of things we encounter. If you can write an equation for it, you can derive that equation implicitly. That means just derive it as it stands with respect to t. And then that creates what's called a differential equation, a place to put in not only x, y, t, whatever values you're given, but you can also put in rates of change that you know. So there's lots of cool things that you can take off and do with this. So the next one here is we're talking about a rocket. So we have delved into rocket science. This is your chance. That and parametric equations, so you can do anything. So here's my little drawing. And it's given us some different information. One of the things in our last video set was, can you draw a picture? Write down everything that you know. So I started with a picture, and I'm kind of putting everything I know in the picture too. And I'll make the t-table of things I know and what I want. So between those two, here's what I see when I read through this. They say that a camera is placed 2,000 feet away from a launch pad. Now, that could be confusing, but it's really meant, think simply like, all right, that's giving you a distance between two locations, the camera being on the left and the launch pad being on the right, and you'd measure along the ground. So think simply with those types of descriptions. So I'm given, if I want to call things horizontal on the ground x, so I called it x equals 2,000. They said the height of the rocket is a function. They called it s, and 50t squared is that function. So I just labeled it in the picture and I put it in my list. And then they said, we're going to do this. Find the rate of change of the angle of elevation when the camera at 10 seconds after liftoff, when t equals 10. And so angle of elevation is how the degree at which you've lifted your eyes or elevated them to look up. So I put theta over there in the corner to show you the elevation, where that would be located in case you didn't know. Those are things that you might not know. So angle of elevation is the angle you look up from a particular fixed other location. In the picture, here's me underlining where I got these things from in the story, color coding it in case you had a hard time finding them. My t-table is ready to go. I haven't written in what I want, which is d theta dt. So I should do that. I will find that. After you get a picture, everything you have and what you want, you need an equation that relates those things. And if I just kind of go in and lightly highlight all of these, the things that I have are the sides of a right triangle, but it's the angle in two sides. And if you remember, that's a trig scenario. That's a right triangle trig scenario. You have an angle in the opposite and adjacent sides from that angle, and that says tangent. And that's from experience. That's a new experience, and so I'm sharing this example to give you that experience. Tangent is the opposite over the adjacent. That's what I have in this picture. It relates to right triangles. I wouldn't use Pythagorean theorem this time because I don't have the hypotenuse. Nobody's giving me information about or asking me about that hypotenuse. Let me get those little dashes out of there, and let's continue on. So now that I have all that together, here's my picture kind of completed, me calling the horizontal distance between those two is an x as x, and then here's my equation. Tangent of theta is 50t squared, the opposite over the adjacent 2,000. Now I put 2,000 in as in last class. I would put that in as x, and I didn't put any numbers in. I'm going to tell you, if you have a value in your original problem that is constant, doesn't change, is fixed, you are allowed to sub it in right away, because when you take the derivative, the things that are fixed don't have a rate of change. They will not have a variable. It doesn't matter what the derivative of that is. So anything that's constant, we can put in right away, because the derivative, there is no rate of change associated with that particular characteristic of whatever the scenario is. So I'll write a little bit more about that later. Any constant you have, things that don't move or change size or length in the problem, can be subbed in right away to the picture and can be part of your relation equation. 2,000, that distance between the camera and launch pad, is a constant, so I've put it in the problem. It'll make the problem easier when you put in things that are constant right away. So then if I do take this and simplify, do you notice that I simplified a little bit? 50 over 2,000 is 1/40th. I did that because I like the derivative of 1/40th t squared better than the 50t squared over 2,000 that I had before. It's kind of like, looks like quotient rule until I simplify a little and go, oh, that's an easy power rule derivative. I got that. And don't forget, derivative of tangent is secant squared. So here goes. Then when you do derive, remember you put d variable dt after it. So when I derive tangent, I had secant squared theta times d theta dt. That's that chain rule. And then when I derived 1 over 40 t squared, I got 1/20th t dt. And yes, that cancels down to 1, but I want to establish that habit. You do d variable dt. We implicitly derive the equation in these related rates examples. And then any cancellations and elsewise, we deal with it. Now we're going to fill in what we know. We know x, we know s is an equation. We're actually going to put the equation in for s if we have it. And you notice we actually don't. There's no place for it. So I wonder how that's going to play out. You'll see here in a minute. And then the next thing I want to do is take the, so here's me. Oh, I wanted to step back a second. So here's what I did. I derived the whole equation on the left. You see the result, the differential equation on the right. And I told you that when there's a constant, it can be subbed in right away because they have zero rate of change, and therefore put them in there. The derivative will work itself out. We don't need to deal with those. We don't have to wait to put those in. We can put in t equals 10. We don't know d theta dt. That's what we want. That's the question mark. dt over dt is 1. Awesome. The secant squared theta is something I can find, or theta for that matter. But usually what we'll do when we have these types of problems is if there's a trig function of theta in these angle of elevation declination problems, we go find that trig function's actual value. So secant of theta is something we can find. Let me show you how. This is a common occurrence. You go to your equation, you go to your triangle that we got in the beginning, and you put in everything you know. Okay, so I said last class, don't put in any values until after the derivative. Today I added a nuance. I said you can put in a value as long as it's a constant. So I did the 2000, but nothing else. I didn't put the 10 in, okay, because 10 is time, it changes. I didn't put in the height of the rocket, that's changing. I didn't put any thetas in, that's changing. Things that are moving, you don't sub in until after the derivative. So now that I've taken the derivative, I'm going to put in everything I know, because everything you know in that triangle could be used to find more things about this scenario. For instance, if I put 10 in for t, I can tell you the height of the rocket. I already know the camera's 2,000 away from the launch pad. I can also find theta if I wanted to, but for this problem, it'd be better if I just found the secant of theta. And do you remember that secant is 1 over cosine? So I could get cosine of theta and then just flip it. And cosine is adjacent over hypotenuse. So 2,000 is the adjacent to theta. Hypotenuse I don't have. So you realize that kind of there's this, okay, if I'm going to get the secant of theta, I need the cosine of theta. If I'm going to get cosine of theta, I need adjacent over, oh dang it, I need the hypotenuse. So once you take the information that you have, you're just going to take and solve for anything else you can find in there. And so let's do this. I'm going to go ahead and just find what I can. I can find the hypotenuse. Remember, it's a squared plus b squared equals c squared. And if you square root a squared plus b squared, you're going to get plain old c. So that's what I did. And that means, oh, my secant of theta, instead of adjacent over a hypotenuse, the 2,000 over that hypotenuse, I'm going to flip it over and do the hypotenuse with that crazy radical over 2,000. So here it is. I wrote those together. That's the secant of theta. That's what I'm going to take and drop in way over here and square it. So that means secant squared of theta. We're going to take that whole thing and square it. So let's pull this on another page. I need more room, but this is just setting you up. I put in everything I know, made a t-table of everything I knew and wanted, got an equation. This was new. We introduced, hey, this would be a tangent scenario because I have an opposite and adjacent and an angle theta. I derived, and we talked about being able to put 2,000 in because it's constant before the derivative. Then once I was done deriving, I started putting in things I know. I realized, dang it, I don't have secant of theta. No problem. Go back and find it with the stuff that we already know. So on to the next page. Let's start fresh because it was getting a little crunched on the other side. So remember where we were. We had found that we wanted d theta dt. We knew t was 10. We knew dt over dt canceled. So I've got all that put in. And then we went and found secant of theta, which we can now sub into it and square it, of course, because secant of theta is what we found, but we're supposed to have secant squared of theta for this equation. So I plugged it in there, and then to get d theta dt, what I'm supposed to find, I just divide both sides by that square root of 2,000 squared plus 5,000 squared over 2,000. So you just see that whole thing. I just divided it over to the other side right there. And by the way, the 10 over 20 is this 1/2 that you see right here. Okay. All said and done, this ends up being about 0.06897, and I did this in radians, so because we're dealing with that's radians per second. That means your eyes would be going up at 0.0689 radians per second following the rocket, at least at that moment in time, after 10 seconds into the flight of the rocket. Now that's abnormally difficult, but I wanted to, while you refresh, I wanted to give you the harder of the related rates problems, just to see that you're still following the same steps. It's just sometimes there's a little bit of old algebra and trig stuff involved in finding missing values required to complete the related rate. The related rate derivative stuff is actually easy. You get the relation equation, you derive it, done, put in everything you know. Sometimes it takes a little bit of algebra to find everything that we have that we can sub into the problem. That's where it got hard. Okay, next round. Let's do a classic. A ladder on the wall of some building, sliding down or going back up. So now this is what I love. These are the kinds of problems where they tell you we want to give students problems that are like real life problems so they can really sink their teeth into it and get intrigued. This is about something that could happen, but obviously not realistic. So please make fun of this as being realistic. I can't imagine ever encountering this situation. I certainly don't want to. I'm on a ladder a lot these days, and the idea of one sliding out from under me is kind of terrifying. So let's play. 17-foot ladder. That's a constant. The ladder is not going to change. So think about, anything constant, I can put it into my equation later right away before the derivative. Everything else, I have to sub in after the derivative. So keep that in mind. And then we'll go, I'm going to call left and right x and up and down y, my triangle. It's a right triangle. There's 3 sides. I bet this is Pythagorean, like the x squared plus y squared equals c squared material, Pythagorean theorem, don't you think? Again, make your t-table. What do you know? And if I go into the problem, they say the ladder's pulling away from the wall at 3 feet per second. If you think about it, that would be making that x, as I've labeled it, I'm calling it x, would be getting bigger. So that's a positive 3. And then it says find how fast it's sliding down the wall. And that sliding down the wall I know is going to be negative. And I don't have the number and I'll solve for it, but I'm anticipating a negative value because if the ladder's sliding down the wall, y will be getting smaller, and that's a shrinking. Okay, so here goes. So, and they also told me, hey, how fast is the ladder sliding down the wall when y equals 8? When it's 8 feet above the ground, that's a y measure above the ground. And then anything about that throws you off, just kind of rewind and look at it or ask me later. But here is, given that right triangle and you have 3 sides, it's definitely Pythagorean theorem. I can derive this. Notice I put the 17 in. Remember, I can put a number in, a value that I've been given, only if it stays constant in the problem. The ladder isn't shrinking in the problem. Then I put in the derivative, which is pretty self-explanatory, 2x dx dt. We're deriving with respect to time here, 2y dy dt. Then I'm able to put in anything that I know, and then if I don't know something, I can also put it in the picture, so I know that y equals 8 and 17 is the length of the ladder. I could solve some of those givens for additional givens if I wanted to. So always be prepared for like, hey, maybe I'll need to find something else out. And turns out, yeah, I actually need to solve for that, the base of that. I need an x. I need something. There's an x in my differential equation, so I'm going to have to go find it from the givens in the right triangle at this point in time. So if I do that little Pythagorean theorem, you get x is 15. You can follow the algebra on that one. And then we start putting things in their place. I just found x, 15. dx dt I got in the beginning, positive 3. Y is 8. The one thing I need to find is now solvable because I have all the unknowns filled in except dy dt. And then we do some algebra from there. So subbing things in, subtract 90, divide by 16, and we get our 45. And it's negative. Now, I think the answer didn't show that in there. I know it's negative because it's a negative 90 when I subtract it, and I know that that's a shrinking value. So maybe it doesn't say, on here it didn't say it, but maybe you should say shrinking. So let's put in here a negative. We're getting smaller by 45/8 feet per second. Decimal is actually kind of nice in this one because it's 5.625 feet per second. In the negative just indicates it's shrinking. To the next round. The boat and the dock. So this is classic. You'll see it on WebAssign, one similar to it. If you can just imagine, it's another right triangle scenario. And if I read through this carefully, the pulley being 7 feet higher than the boat's bow, you'd measure height above vertically. So 7 is the height there. I could have inverted the triangle so that the straight side is right above the boat itself. But I kind of like having the rope at an angle of the pulley like that. So that's just how I chose to draw it. They told me why 7. The rope is being pulled in at 4 feet per second. The rope is slanted. It's the C, and I just called it C because I like hypotenuses to be C. And they told me how fast is the boat approaching when the distance from the rope, how far the rope is out, which is my C length, is 25. So I wrote that in. And then what it wants me to tell is how fast I'm approaching the dock, which is X is your distance from the dock. Dx dt is the rate of change of x. It should be negative, right? Because if we're approaching the dock, it will be getting smaller. X will be shrinking. So I'm anticipating this. Just like dc dt is negative because the rope is being pulled in, it's shrinking its length. Let's get the equation. Little Pythagorean theorem, same as before. Do we have any constants? Anything not changing? Yeah. How high the boat is, or how high the dock is from the boat. That's 7. I put it in. You derive. And this is the equation with its dx dt and dc dt respectively. We can plug in definitely the y. We don't have a y in the equation, so what do we have? We don't have x, but we could find it, right? Dx dt is the one I want to find. C is 25. Dc dt is -4. So those are all good. Let's go find that x, because it often happens. We have 7 above, 25 foot of rope. We could find x is 24. We can sub it in now. And then if we do, it's a pretty quick run to the finish. We divide both sides by 48, about -4.16 repeating, 25/6. Again, they don't write negative in this little magical key on here, or me or whoever. But it is shrinking. It's definitely approaching the dock. The negative indicates that dimension of x is getting smaller. So there you have it. All those are helpful starters to this related relates business. The next thing we'll do in the next video is optimization. So get excited. But related rates, we'll do more of these, but I just want to give you a little bit at a time so it starts to sink in.